This is a rewording of the proof a second loop is impossible in the Collatz Conjecture, which I proved in April 2023, reworded in a different way so maybe people who had difficulty following it the way I had it written can now understand.
This is absolute mathematical proof that a loop is impossible in the 3x plus 1 problem, the Collatz Conjecture, which holds for every possible sequence within infinity.
And in this proof, I term every 3x plus 1 as y. In order to have a loop, every value of x in the loop must have all the rises and descents between it leaving and coming back to itself must cancel out with each other to leave a value of 0. In other words, they must have a net rise of 0.
I prove this impossible in 5 steps of deduction.
Step 1. Between the first x, the lowest x in the theoretical loop, which we call xn, and 3xn, we have 2xn, which we can cancel with 2xn between the final y, which we call yf to xn, which is coloured red in the image. This leaves a net fall of yf minus 3xn between the final y, yf, and xn. Y is always even, 3x is always odd, so y minus 3xn is an odd number. Step 2. So now we know we must get a net rise of an odd number between the first y, 3xn plus 1, and the final 3x, which is 3xn minus 1, which must be exactly the same value as yf minus 3xn. So one cancels from the other to leave a net rise of 0 between xn leaving and coming back to itself. That net rise and yf minus 3xn coloured yellow in the image. Step 3a. In the case where the value of x is higher than the previous x, which we call xh, there is always one x in the descent from y to xh and 2xh between xh and 3xh. So we can cancel 1xh from y to xh with 1xh between xh and 3xh. This leaves a net rise of 1xh between y to xh to 3xh. This is always a net rise of an odd number. 3b. In the case where the value of x is lower than the previous x, which we'll call xl, there is always an odd number of x's from y to xl and 2xl between xl and 3xl. So we can cancel 2xl in the rise from xl to 3xl with 2xl in the descent from y to xl. This always leaves a net descent of y minus 3xl between y to xl to 3xl. Step 4. This means we need either a, an odd number of net descents subtracted from an even number of net rises between the first y, or 3xn plus 1, which we will call yn, and the final 3x, which we will call 3xn minus 1, to leave a total net rise in an odd number, which must be the same value as yf minus 3xn, so that one cancels from the other to leave a net rise of 0 between xn leaving and returning to itself. Or b, an even number of net descents subtracted from an odd number of net rises to leave a total net rise of an odd number between yn and 3xn minus 1, which must be the same value as yf minus 3xn, so one cancels from the other to leave a net rise of 0 between xn leaving and returning to itself. Step 5. However, here arises an unavoidable inequality. For such a loop to exist, each and every x in the loop must have a net rise of 0 between leaving and returning to itself. So we know if xn is the lowest value of x in the loop, then the next x, which is xn plus 1, must be higher, 1.5 xn plus 0.5 times higher to be exact. So the difference between 3xn plus 1 and yf, which is yf minus 3xn plus 1, will also be an odd number. Yet now we have an even number of net rises and descents between yn plus 1 and 3xn minus 1. This would leave either an odd number of net rises and an odd number of net descents, or an even number of net rises and an even number of net descents. So when we cancel one from the other, we'll be left with a net rise, which would be an even number between yn plus 1 and 3xn minus 1, which cannot cancel with yf minus 3xn plus 1, which is an odd number, to leave a net rise of 0 for xn plus 1 to return to itself. If it were a case where yf is only 4xn and lower in value than 3xn plus 1, then xn minus 2 would still be higher than xn, which is the lowest x in the hypothetical loop. So the difference between the third last y, yf minus 2, and 3xn plus 1, i.e. yf minus 2 minus 3xn plus 1, will still be odd. Yet we would still have a net even rise between yn plus 1 and 3xn minus 3. So if xn had a net rise of 0, then xn plus 1 could not have a net rise of 0 and return to itself. So such a loop cannot exist. so it's impossible to have a second loop in the Collatz conjecture for any sequence within infinity. Proven by me, Sean Anthony Gilligan, in April 2023, with this revision on the 12th of July 2024. Lots more long-standing problems in maths and physics solved on my YouTube channel, Breaking Physics Beyond the Standard Model, and odyssey.com, Science Not Dogma. And in my theory of everything.